So let's start. Today we are going to finish off talking about group theory. And I have suggestions from some students about how they want to learn about non-Euclidean geometry. Although I'm not really knowledgeable on that topic, I thought maybe topology or knot theory might be a good substitute for that. So if we have time, we might talk a bit about topology and knot theory, or we could solve an interesting question on search that Mr. Robbins has brought. So if we have time left, let's just run a vote and see which ones you guys want. So today, first, we're going to have a recap on what we did last time, and then like a math starter where we talk about chessboards, and then finally we're going to talk about Rubik's cubes. So does everyone know what a Rubik's cube is? Does anyone like playing with Rubik's cubes? Is anyone like those people that do really fast? Is anyone like your friends? Yeah. So hopefully, I think everyone knows about Rubik's cubes. So let's first recap what we talked about last session. Last session we talked about cycles of a group, about how if a group is finite, about how the elements in a group is finite, and we call that cardinality in fancy terms. But still, if the element of group A is finite, so if it's not infinity, then an element of A would have a cycle because it has to come back to itself, or else it's going to be infinite. That's what we mainly talked about last time regarding groups. And then we also solved the peg solitaire question, where we kind of used the notion of groups and tried to prove how in some situations putting the peg in the middle is simply impossible to do. Does anyone remember how we solved this question here? You can just shout it out. No one?
X, Y, Z.
Yes, right. We named it like X, Y, Z, Y, X, Z, Z, X, Y. And then we applied group theory in order to prove that the sum of all the X, Y, Z's on the cubes here is something called an invariant, which is something that never changes, and therefore, no matter what kind of movement we do, the sum is going to stay the same, and therefore, it is possible to put the peg in this location, these 5 locations. That's what we basically proved last time. I'm going to upload resources and notes of these on Google Classroom later. So if you don't remember, you can just refer to your notes in your free time. So that's it about the recap. So I want to do a quick math starter about the chessboard. So in a chessboard, does anyone know how many rows or columns we have?
8 and 8.
Is it 8 and 8? Are you sure it's 8 and 8?
Pretty sure.
Okay. So in a chessboard, so my question is this. So let's say that there's actually it doesn't really matter. Let's say that there's an 8 by 8 chessboard here. So we have black, white, squares all around. Then if we have a domino, which is basically a block that looks like this, we have an infinite number of dominoes. We have lots and lots of dominoes, and you can separate this into 2. And then each of these squares here have the same size as this. So you can place this on here, and it will take this amount of space. Then, is it possible for us, let's actually change this to 9 and 9. Then is it possible for us to, that was stupid, we should wait. Then is it possible for us to place the dominoes on this chessboard so that every single square is filled with this domino without the domino overlapping with each other? Is that possible? Wait, that's also a very stupid question.
Here you go, Gina.
Oh, okay, I'm sorry. Actually, the question is, if we take out this block here and this block here, so eventually if the shape is like this, so essentially it's supposed to be 8. We took 2 out from here. We cut the chessboard so that these 2 squares no longer exist. Then is it possible for us to arrange the dominoes on this chessboard so that the dominoes do not overlap, but every single square is filled with this domino? Is this possible? You can have some time to think, maybe like 10 minutes. And as a general hint, it's kind of similar to Peck Solitaire. And another hint is that pay attention to the color of the squares. So you can talk with your table, have some time to think about this question.
I think that's probably.
Nothing works.
The teacher was just counting up the marks. Oh, good idea, girls. You can draw on the big boards if you like. Lucy, you girls can draw on the big board.
That's the correct solution. So what he talked about is, so the key to solving this problem is that in a chessboard, you have alternating black and white squares, which means that no matter how you place a domino onto here, because the domino has 2 squares, one is going to be black and the other one is going to be white. If we place this the other way around, it's still going to be, one is going to be black and the other one is going to be white. So because this is a 2x1 domino, and because we have black and white alternating squares within the chessboard, no matter how we try to place this domino onto this chessboard, we're going to have 1 black and 1 white on this 2x1 domino. And then, if we remove 2 of these squares from the original chessboard, we start with black here, right? So black, white, and then here, the last one is going to be white. So we took out 1 white square from the original chessboard. Here, this is also black, white. So here we also took out a white square from the original chessboard, which means that we had 32 blacks and 32 whites at the start, but now we have 32 blacks and 30 white squares. And because when we place a domino onto this chessboard, it takes up 1 black square and 1 white square. If something can satisfy this condition here, the number of black squares and number of white squares have to be the same, right? Because if you have like 4 black squares and 2 white squares, it is impossible for you to put dominoes that have 1 black and 1 white onto this kind of configuration. So here, the same thing applies, and because you have different number of black squares and white squares, we get the results that using a 2x1 domino is just impossible to put down here. But then what we can also know from that is this one's black and this one's also black. So if we take out these 2 squares instead, maybe this might be possible. yeah, it will be possible. So in essence, this is really similar, although this did not use group theory, this is quite similar to what we did last week, right? Because in Peg Solitaire, we set something that never changes, and then we use that characteristic to determine whether a certain configuration is possible or not. And again, in here, we found something that never changes no matter what, and then we use this characteristic to our advantage. So that's like the similarity between what we did last week and this chessboard problem here. Any questions? Okay, I guess no questions. Then let's talk about the Rubik's Cube. Does everyone know who here has never seen a Rubik's Cube before? Oh, okay, nice. So a Rubik's Cube is a 3x3 cube that looks like this, where each side has different colors. I'll put this side as white, this side red. So all these 6 sides have different colors on it. And it's a 3x3 cube where you can twist, or where you can twist each of these, this one here, this one here, or this one here, or this one here. You can twist those and then make it into a different kind of shape. So I hope everyone has seen this at least once in their life before. Because if not, it will be very hard to explain it in only version of videos. So this is basically what a Rubik's Cube is. And there are many techniques to making this cube back to what it actually was. So there are many techniques to make this cube back into a shape where each of these sides have the same colors. And one of the techniques have an average number of 100 moves, while the other ones have an average of 56 moves. So the question here that mathematicians found with the Rubik's Cube was that no matter how we mix this, no matter how we spin this around, what is the minimum number of moves that's required to change that some kind of messy Rubik's Cube back to this. So no matter how you mix this, there's going to be a certain number n, which is the upper bound, and all the ways in which you can change this back to here, the minimum number will always be smaller than this number n, and we call this God's number. Because mathematicians thought that if God existed, he would probably know what this number is, and that's probably a very bad way to name something. So, before we talk about what God's number is, we can't just prove this using our hands. We need a really, really, really good computer. Even like the mathematicians used really advanced algorithms, and they still used almost all the computers in Google, and it still took them several weeks to compute all the things. But there are ways for us to make the computing much, much easier. And that's what we're going to talk about. And that involves group theory. So we will denote the method to change this into this using group notations. So this side, so we will name each of these sides first of all. Let's call that set X. So the side on the upper side, because the upper side we're going to call it U. This side front, this side back. Oh no, let's actually just call it A, B, C, D. So this is what we're going to call each of these sides. Do you remember that I told you that sets do not only consist of numbers, but they can just consist of like virtually everything. So here we will call each of these sides are going to be elements. So this is how we're going to name them. This one is A, the bottom one is F, B, D, C, E. This is how we're going to name each of the sides. And then when you make a Rubik's Cube back into here, when you match your Rubik's Cube, if you twist this side by 90 degrees clockwise, we will call that C1. Computing C for one time. And then if we do that 2 times, which is twisting it clockwise by 180 degrees, we're going to call it C2. And if you do that 3 times, it's going to twist it by 270 degrees clockwise, and you're going to call it C3, and this is going to be same for C minus 1, which is the inverse of C, because if we twist C 4 times, if we twist the same side 4 times, it's going to come back to itself. So here, C4 is C, and the order of this thing here is 4. So this is what you can this is how we're going to denote the way of matching this Rubik's Cube here. So if you first start with twisting side A 2 times, you're going to denote it as A2, and then after that, if you twist B like 1 time, that is B, C anti-clockwise once, C minus 1, and then maybe like you want to do A once again, then you're going to denote that as A, and then this is how basically we're going to denote the movement of this cube. Okay, everything clear? So using this kind of group notation, I'm going to soon show you how we can simplify this process. But before we go into that, let's first talk about how many combinations of matching this cube is, because we just want to get a general gist of how long the computing is going to take. Okay? So to consider all the possible combinations of this Rubik's Cube, let's consider dismantling this entire thing. So if you dismantle this, you'll get 27 of these small cubes, I'll call them cubicles, and then depending on where you are, 3 or 2 or 1 size of the cubicle is going to be colored. If we took this one here out, 3 sides will be colored, while if we take this one out, 1 side will be colored, and here we will have only 2 sides that are colored. So we're basically dismantling the Rubik's Cube and trying to put back into a shape where we determine how many ways are there to actually put this back into the original cube together. So how many cubes will there be with 3 colors? Can anyone answer this? Yes, correct, 8, because each of the corners here are going to have 3 colors, and there are 8 of those. What about 2 colors? What about 2 colors then? No, 12, yes. And finally, for 1 color, because you're only talking about these ones here, it's going to be 6. Right?
It's
27. Oh
27.
yes, it's 26.
Yeah.
Yes. So, and then let's just take out the center one because that's just useless, right? That doesn't affect our combination of this. So when you're putting back into this again, let's consider this one first. We have 8, which means that we can arrange them into either this. So we have 8 of these 3 colored cubes. Then let's choose which of these corners that the first one among these 8 cubes is going to go to. So we have a set of these 8 cubes. Let's just choose one, and then let's determine where this one is going to go to among these 8 corners. There are 8 ways of choosing this. The next one 7, the next one 6, all the way up to 1, correct? But we have to consider rotations. So we use this as a fixed point. We say that this is just fixed at here, then we won't have to consider the rotations, right? So we just take this 8 out. So the total number is going to be 7 times 6 times all the way down to 1. But then we also have to consider the direction, like the orientation of these cubes, because all of these 3 colors, all these 3 sides have different colors. So if this side here is white, this side here is red, and this side here is blue. Let's say that we put this on this corner here. There are 3 ways of flipping this around, right? There are 3 ways of spinning this. So for each of the 3 colors, we have 3 ways of doing that, which means that we will multiply 3 to the power of . Is it unclear? Is anything unclear until this stage? Okay, 3 to the power of 8, right? Because we're placing these cubes onto each of the corners, and then we're deciding the direction after you choose where each of the cubes are going to go to. Okay? So this is basically for the 3 colors. For the 2 colors, we do the same thing. So you choose where these 2 colored cubes are going to go to, and then we choose the orientation. Which means that by the same logic, we decide, so the first one among these 12 cubes have 12 places to go, the next one has 11 places, and the next one has 10 places, so on, so on. And then we decide the orientation by just multiplying 2 to the power of 12. And then for the final one, we have 1 color, and then here, times 5 times this, and then the orientation doesn't matter because we only have 1 color, and if you have only 1 color, the direction won't really matter, right? Because we have only 1 direction. But then the really important thing to note here is that if this side is white and this side is yellow, if you choose only where the white one is gonna go, the yellow one is just automatically decided. Because these 2 never change. Because these 2 are always facing towards each other, and no matter how you twist the cubes, the white centered cube is still going to face the yellow centered cube, right? So if we choose only this one here, the other one is going to be just automatically decided. Which means that we don't have to multiply all of these, right? Because if we choose only 3 of the ones among these 6 cubes, the other 3 is going to be automatically decided, right? But then if you also think about it, if this side here is white, and this side here is, let's say, red, and let's say this side is blue. Let's say that we started with this configuration. No matter how we twist this cube, these 3 are going to always stay the same. Like, no matter how you twist it, these 3 orientations, so like white here, and red here, and blue here, this is never going to change, right? So this means, oh, sorry, not this one. So let's say that the blue one is here. This orientation never changes, which means that we also don't have to consider the 5 here, right? Is this clear? Like, this is very unclear when I try to explain it at first, but if you have a Rubik's Cube at home, you can just try it yourself, and you'll see that if you choose 2 of these centered cubes, the other 4 are just automatically decided. And then in here, the other thing to note here is that let's say that this Rubik's Cube is already matched. So each of these sides have all the same colors. So like this side is white, this side is red, and this side is blue. But if this cube is already matched, and then this side is red, and this side is blue, well, if we change only this one, so that this side here is blue and this side here is white, it will be impossible to make this into this kind of configuration, right? Because no matter how we try to twist this around, this is going to still stay the same. This means that if we choose the orientations for 11 two-colored cubes, the other one is automatically decided, right? Because if we started off with this kind of configuration, we would never be able to obtain this one here. So we also take one out from here. And then here, using the same logic, this also becomes 7. Because if we had a totally matched cube, we can't just spin this by 90 degrees, or like, we can't just twist this by 120 degrees or 240 degrees. Then it would be impossible to match this back into this kind of shape. So this is basically what we have to multiply. And if we multiply all of these together, we get a really, really big number, which is 4.3 billion, I think. But there's still a way to make this computing much easier so that our computers can do this. Because we don't have to consider rotations or reflections of this Rubik's Cube here. If we could change this shape back to this shape, if we rotate this by 90 degrees, we will still be able to rotate that back into this kind of shape, right? Because we can do the same types of moves, just as rotated by 90 degrees. Also, by the same token, if this shape here is rotated by 180 degrees, if we did the same moves, just rotated by 180 degrees, we will still get this shape here. So we don't have to consider the rotated ones. So the rotation, so the ones that become identical when you rotate it by 90, 180, or 270 degrees, we can just cross all of those out. That applies to each of the sides, which means that for each of the sides, 4, because we can do 4 rotations, because we have 6 sides, 6, and then when we consider the reflections by this axis here, we multiply 2, which means that we basically have 48 shapes that are just actually the same, that just have like the same solution, just as rotated or reflected, right? So we multiply 1/48 to this number here, because we don't have to consider the other 47 solutions, because they're just the same thing, just as reflected or rotated. So, and then we split this into different groups, and then develop an algorithm that determines whether each of the configurations can be switched back into this within 20 spins. And then computing that with like really good computers, we eventually get the number that Gauss number, which is the minimum number, just equals 20. So this is how mathematicians proved it. You know, it was very unclear to explain the twisting of the cube in words, but you can still find the videos on YouTube, and they're going to tell you about, and with visual aid, it'll be much more easier to